got a PhD from Seoul University, and he has a brief time as a postdoc there, and moved to the US University. He's working on turbulence, MHD, and submesh. And so he will be the first speaker today.
Good morning, everyone. My name is Chang-Goo from Western University. Actually, this name changed from the original name, University of Western Ontario recently. So I'm working with Professor Santon Basu and about the decaying MHD turbulence in the multiphase industrial medium. So actually, there are well-known classical turbulence theory especially for the incompressible turbulence. In 1941, the Chang-Goo developed the theory for the incompressible aerodynamic turbulence. He showed that the steady state of the turbulence make this kind of one-dimensional power law, and energy dissipation here eddy cascading from the larger scale to the smaller scale that transfer the energy all the way down to the viscous scale and energy dissipates. Also, 1995, Ulrich Schrieder developed a very good theory for incompressible MHD turbulence. So with the magnetic field, the eddies are elongated in the direction of the field, but essentially it's the same mechanism for the energy dissipation. However, the compressible and MHD turbulence is really complicated, so it's not easy to develop an analytic theory, so it requires nonlinear simulation. Mainly because it contains a nonlinear phenomena like a shock, and shock provides additional dissipation. So people think even in compressible MHD turbulence, also turbulent energy decays very rapidly. But someone suggests an idea when there is strong magnetic field, then some linear Arcan waves survive and it provides turbulence. And or it observed as an abnormal motion in ubiquitously observed supersonic, and can explain the supersonic velocity dispersion in industrial medium. But recent numerical simulation for compressible MHD turbulence reveals that that kind of belief is not really true, because this in their nonlinear simulations, even compressible MHD turbulence decays very rapidly as hydrodynamic turbulence within a flow burst time. Also, other groups show that this type of independence of the magnetic field strength, and usually the turbulence decays as a function of the T3-1 power. So compressible MHD turbulence dissipates very rapidly within a flow burst time, and it is really independent of the field strength and details of the initial population shapes. So recent local and isothermal simulations shows the turbulence energy dissipates very rapidly with this type of power function, and independent irrespective to the field strengths. So now the turbulent community actually focus on what are the turbulent drivers to explain the ubiquitously observed the supersonic turbulence. However, please keep in mind that this kind of local simulation represents a local patch of the homogeneous cloud. So it is really applicable to the molecular simulation within the molecular cloud, but the real industrial medium, especially for the neutral industrial medium, is not really like this type of homogeneous structures with the isothermal indication state. So the question is it really applicable to the neutral industrial medium? So let's look at the detail of the industrial medium. So the neutral industrial medium is really consists of the cold neutral medium and warm neutral medium with two order of magnitude difference between two mediums in temperature and density. Cold neutral medium clouds are usually observed as sheets rather than isotropic clouds, and the mean magnetic field strength is really strong. So usually, compared to the thermal energy, it is sub-equipartition, and turbulent energy, it is really equipartition. And the Mach number, sodium Mach number is about 3, and Artin Mach number is about 1 for the cold medium. The field orientation is quite uncertain, but the perpendicular field to the ship is slightly weaker in observations. So velocity, turbulence velocity, so also the isotropic and anisotropy of the turbulence is still questionable. So listen to two-dimensional, very simple simulations by Basu and Deb show that two-dimensional thin sheet simulations shows quite long-lived turbulence due to the magnetic tension driven mode, driven by global magnetic field effect. But in their simulation, they only consider two-dimensional sheets, but assuming the vacuum bound or vacuum outside in vertical direction, and in this vertical direction, magnetic fields instantaneously redistributed to the potential field. So the assumption is quite good. So it is required to model this type of thin cold medium shape within the one neutral medium in full three-dimensional simulations. So now we develop full three-dimensional simulations with interstellar cooling and heating, construct two-phase interstellar medium. The initial condition is like that. We have a 20 parsec cubical box with thin cold medium sheet at the plane. And magnetic field is either vertical or also we run models with a positive magnetic field that is parallel to the ship. Initially, gas in the pressure equilibrium with this type of this amount of thermal pressure that gives this two-phase equilibrium medium. The magnetic field is initially uniform with plasma beta parameters 0.1, 1, and 2. So this, I will call this one the strong field case, intermediate field case, weak field, and hydrogen case. Velocity field perturbation is has power type this shade with a peak at wave numbers 8. This gives a similar peak wavelengths with the thickness of the cold medium sheet. And we also consider isotropic or anisotropic turbulence. Here we call the isotropic turbulence with the velocity amplitude in all directions is the same as 2 km per second. For anisotropic case, we the vertical motion is there is no vertical motion for the anisotropic case. So here I will first show you result from the anisotropic strong magnetic field perpendicular case. So here you can see the Coulomb density map in x, y, x, g, y, z plane. The magnetic field is vertical here. And here you can see the time evolution of the kinetic energy in total and in perpendicular direction and in parallel direction. Let's one more time.
There's no gravity in perpendicular and parallel with respect
to
magnetic field?
We didn't consider any gravity.
Okay, and perpendicular parallel with respect to magnetic field?
Yeah. No, so here this perpendicular and parallel is the perpendicular to the magnetic field direction. And in this case, the perpendicular of the magnetic field is perpendicular to the ship, cold medium ship. Sorry for confusion. So anyway, you can see the initially rapidly decaying turbulence in this kinetic energy evolution. But at later time, it's not keep decaying, and it has quite a significant amount of energy. At later time, it's about 20% of initial energy survives within about 40 flow constant times. And at this motion is really, this kinetic energy really comes from the long-lived incompressible motion in XY plane. At later time, so our model is not isothermal, so it is good to see the magnetic number PDFs to show what, how much fraction of the gas are really in supersonic release.
Sorry, can I ask you a question just on that last slide?
Okay.
The incompressible motion there, is that interchange modes?
No,
because it's a strong magnetic field, you said it's in the XY plane. So
actually, this incompressible mode is really kind of vertical motions. So it's, I'm not sure if we can say that it comes from the interchange mode. I think we think it comes from the linear arcane waves, the incompressible transport arcane waves. So even at after 10 or 40 crossing time, there are significant amount of gas, cold gas is in supersonic region, but they are really in subarcanic region. So that's why we believe that linear arcane waves survives longer at later time. So at very rare time, the turbulence velocity or velocity dispersion is about 1 per second. But all gas are in subarcanic region. To see the magnetic field strength dependence, we run 4 different models with this type of anisotropic perpendicular model. So here you can see a clear dependence of the magnetic field strengths. For intermediate or field strength, it still has some amount of energy, but for weak field case, it's really similar to the hydrodynamic case, and the turbulence energy keep decaying as T to the minus 1 shape. For the parallel field case, the evolution is really different. So just keep looking at this kinetic energy evolution, you can see both parallel and perpendicular components keep decaying. Turbulent energy keep decaying as T to the minus 1. There is no later time surviving energy. But the structure is quite complicated. It's not really our main focus, but mainly this type of structure is developed by the Canonical type instability at the contact discontinuity, initial contact discontinuity due to the velocity difference and density difference. For this case, actually, there is no dependence on the magnetic field strength. All models shows the kinetic energy is keep decaying, as in the hydrodynamic models and also as in the previous local isothermal simulations. For this case, we consider the isotropic velocity dispersion. Then there is an initial additional turbulent energy in vertical direction. So the sheet-like structure doesn't maintain it dispersed in the vertical direction due to its initial turbulent energy imbalance. But you can see the parallel component, which means the vertical motions are keep decaying as similar power, but the perpendicular motion has this type of turnover as shown in the previous anisotropic models. So, and also this type of perpendicular motions are only shown in the strong magnetic field case. So this type of the incompressible motion-driven later time turbulence is strongly depend on magnetic field strength and magnetic field orientation. So in short conclusion, the MHD turbulence decays rapidly as in previous isothermal simulations at early stage and for the compressible component, but the incompressible component can survive longer and has quite a significant amount of energy for the cold neutral medium sheet with a strong perpendicular magnetic field. So this type of the cold neutral medium sheet with the perpendicular magnetic field is how this kind of cold neutral medium sheet can form from the interstellar medium. So here is one clue from the colliding flow of simulations for warm neutral medium. These simulations, assuming the warm neutral medium flows that is supersonic, and then when they meet, they form a shock and from cold neutral medium sheet in direction perpendicular to the flow direction. So here, these two panels shows the case for the magnetic field is parallel to the flow direction, which means here the magnetic field direction is this direction, and flow also converge in this along this direction. Then they form in cold neutral medium sheets. But for the when the magnetic field strength is not so strong, then it easily dispersed by the nonlinear physical instability. But when the magnetic field strength is quite strong, then it can survive longer and form the cold neutral medium sheet with perpendicular magnetic field. When the flow direction is perpendicular to the magnetic field, then in the case of the strong magnetic field, the formation of the cold neutral medium is prevented by the magnetic field because the flow cannot hardly move across the magnetic field direction. Only weak field case can form this type of cold neutral medium sheet, but it also easily dispersed by the nonlinear physical instability. So that kind of the supersonic colliding flow is believed to be reported. So then cold neutral medium sheet maybe formed in perpendicular direction to the magnetic field. Perpendicular to the direction to the magnetic field. We think it's preferred in this type of colliding flow simulations. And also there are some observations for actually this one is for molecular cloud. But this type of molecular cloud also found in the filamentary and shoe-like structures with this type of perpendicular magnetic field. So it is easier to form the sheet and field filaments in direction perpendicular to the magnetic field rather than the parallel to the magnetic field. So it is believed that filaments and sheets are really ubiquitous. Then if this type of sheet, for the formation of this type of sheet and filaments, we can think the strong perpendicular field to the cold neutral medium sheets are preferred in the neutral interstellar medium. Also, in the molecular cloud, you can expect this type of structures. So the local isothermal simulations are really good, give a really good theory for the decaying turbulence, but at larger scale, for the neutral medium, we think that the global effect of the field structure and field structure and velocity structure should be considered in the decaying MHD turbulence. So in this case, the cold neutral medium sheets maybe have anisotropic turbulence velocity field structures. Okay, thank you very much.
So we have some time for a few questions. Stephen Green is going to set up this laptop. Yeah, do you have any questions? Yeah.
So one thing, I mean, it was a little hard to see from your movie, but the power spectra of the late time turbulence, does it look like,
so actually,
or is it dominated by?
Yeah, actually I prepared that, maybe I thought this not good to show within the time. triangle. So here I draw a power spectrum for incompressible mode, which is in the solid line, and dashed line shows the compressible mode. The black is initial turbulent power spectrum. As time goes by, the large scale incompressible motion actually grows, but all at later time all follows kind of power law shape. Actually, it's really similar to the type power spectrum, and its incompressible mode has two other magnitude compared to the compressible. In vertical direction, we actually developed a symmetrically average power spectrum energy for the compressible and shearing mode. And you can see that in the middle plane, which is in the cold medium, compressible mode has more energy compared to the high latitude, but it still have just 1% of the incompressible mode. So many incompressible mode is dominated. And for different cases, you can see that this one is so these two are might field is perpendicular to the shape, and the middle red line is might field is parallel to the shape. You cannot see the that such an increment of the incompressible motion for when the field is parallel to the shape. But when the field is perpendicular to the shape, you can see the high actually grow over the incompressible mode in this case.
So, all this incompressible power you have you done a wave mode decomposition, right? Say, like, showing those areas?
Yeah,
then you can tell if it's actually interchange around Feynman.
Right. Actually, it's really good, promising to see that kind of wave mode decomposition rather than this kind of compressible and shearing decomposition. Because our initial condition is not really homogeneous, so it's not really good to applicable that kind of wave mode decomposition because it's assuming some
There's a fancier way to do it with wavelets as well.
Yeah, it could be considered. Yeah. I think it's yeah, we can talk. Yeah, discuss something. Yeah.
Okay, so any more questions? We move to the next speaker, which is Stephen Green from University of Prague. He was undergrad student here at the University of Toronto, and he moved to Chicago for his PhD. And his thesis was on the cosmological fact reaction in general relativity. And now he's working mainly on the stability of relativistic fluids and fluid gravity relativity. And today he will tell us more about this research.
So I'm going to be talking about the relationship between dynamic and thermodynamic stability of perfect fluid stars, and this is work with my former advisor and his current students. So I'll begin by introducing some previous work which provided some motivation where Bob and Stephen Holland studied the black hole and black brain case. And then I'll introduce the Einstein-Perfect fluid system, which I'm going to talk to now. And we have to use this Lagrangian framework to use the method, so I'll have to introduce that. And then I'll derive a dynamic stability criterion for perturbations off of stationary axisymmetric solutions like stars. And then I'll show how this is related to the thermodynamic stability. So a priori, there are two different inequivalent notions of stability which are relevant for astrophysics. First is the actual notion of stability, dynamical stability. That is, if you perturb a system in equilibrium, will it grow in time or will the perturbation be damped? But this is non-trivial to analyze directly since equations of motion can be quite complicated. So often thermodynamic analyses could be simpler, where we ask, is the configuration at a maximum of entropy for the given state parameters? But it's not necessarily true that if something is thermodynamically stable or unstable, that it applies in the dynamical case, because the equations of motion may not allow you to, say, increase your entropy, even though thermodynamically it seems possible. So, like I said, Holland's and Wald established an equivalence for black holes and black brains, and we're going to extend it to perfect fluid stars. So their result for black holes was that dynamical stability is equivalent to the positivity of this canonical energy quantity E on a subspace of axisymmetric linearized solutions which do not change the first order of the ADM mass, linear momentum, and the angular momentum of the solution. And furthermore, this canonical energy is then related to second order, these second order changes in these quantities, which basically tells us, the sign of this quantity tells us whether entropy is at a local maximum or minimum. So by evaluating this, which is often easier to evaluate, we can learn about dynamical stability.
It's connected as
Oh.
so as
Seems to plug in.
Am I just plugging on the later?
It's not clear on that, but
Yeah, well, I think maybe because it got like disconnected for a minute.
okay. Can people read that? Okay.
Yeah, no, it's just on.
It's just that it's recorded.
Oh, okay.
Okay.
Yeah, so how does this make the analysis easier? Well, I'll look at the, say, Schwarzschild black hole, where the area is equal to m squared. So we could consider a family of perturbations where we vary this parameter lambda to change the mass of the black hole. Now, this isn't allowed, but I'll come back to that. But you can plug in this sort of perturbation and easily evaluate the right-hand side to find that E is negative. So this suggests an instability. But of course, Schwarzschild is stable. And if you remember, we weren't allowed to change the ADM mass. And that's why we're not allowed to use this. But so this tells us why Schwarzschild can have a negative specific heat capacity but still be stable. But on the other hand, you can apply this to the Schwarzschild black brane, which is the black hole just across R. And you can imagine a perturbation of this form where you make it wider in one region and narrower in another region, and keeping the total mass fixed. And what this region becomes hotter, this region becomes colder, and it's a runaway process because more energy will flow in that direction. And it's a much easier analysis than looking at the linearized perturbation equation. So what about perfect fluid? So the approach taken to prove the above results for black holes and black branes is based on a Lagrangian formulation of vacuum relativity. And since we can formulate relativistic perfect fluids in terms of a Lagrangian, we should be able to apply the techniques and obtain a result relevant for relativistic stars. So, but there are two major differences. First off, it's much easier because we don't have to worry about any horizons involved, and that was a big complication in the original work. On the other hand, Lagrangian formulations of perfect fluids are quite complicated because you can't express the formulation in terms of the physical fluid variables like the density and stuff. Instead, you have to introduce these potential fields, which I'm going to call the dynamical variables. And in particular, stationary configurations may not be stationary when you write them in terms of dynamical variables. And that means that certain techniques don't carry over and you have to figure out how to get around it. And you also introduce additional gauge freedom, as you often do when you introduce potential fields. So the goal then is we're going to consider a stationary axisymmetric solution to the Einstein-Perfect fluid equations, and we'll let delta phi be a linearized perturbation off of the background. And we wish to determine a class of perturbations, I'm going to call T, for which the dynamical stability can be determined by use of the canonical energy. And then we want to relate that to the thermodynamic quantities. And then see if these two notions are equivalent. So this should be familiar. We're going to describe perfect fluids by a metric, a form velocity, particle number density, and an entropy per particle. And then when you add an equation of state and the first law of thermodynamics, then you can work out all the other fields in terms of these. And we write down our perfect fluid stress energy tensor, and our equations of motion are just the Einstein equation, conservation of stress energy, which of course follows from the Einstein equation, and conservation of particle number along the world length. So I'm not going to use these variables anymore. I'm going to have to introduce some new ones. So this is, well, before I do that, I'm going to replace the fields U and N by this free-form NABC, which you can just extract N and U from that. It's just more convenient because then conservation of particle number is just N is closed. And I'm going to denote these three physical fields by Q. But now we have to introduce our new dynamical fields, which John Friedman did first in 1978. And so to do this, we have to, it's a somewhat complicated construction because we have to introduce a new fiducial manifold F, where we define these fixed tensor fields, N and S, on this manifold. And they have to satisfy this constraint that N is closed and N wedge dx is equal to 0. Don't worry about that too much. But then the dynamical fields are the metric and a mapping from F to M, which we collectively will denote phi. So G and chi, this diffeo are a field. And then our Lagrangian is the Einstein-Hilbert Lagrangian, and our matter Lagrangian is minus rho times, this is the volume form. Another thing I have to point out is that I'm not treating Lagrangians as scalar densities. I'm treating them as four forms. Everything's equivalent, but it's more convenient. So in pictures, what we have is we have our fiducial manifold. We have N and S defined on this manifold. We map it with chi onto a new manifold where we also have a metric. We just push forward these fields. And then what this does is it does restrict to configurations where the baryon number and the entropy per baryon of each fluid element is preserved. Of course, since we want to vary our Lagrangian, we want to vary our field configuration. So we have to introduce a new one-parameter family of diffeos, which depends on the parameter lambda, and again pushes forward our fields. You can think of this diffeo as just moving around our fluid elements, but not adding new fluids. Now, to first order, a one-parameter family of diffeomorphisms is generated by a vector field. So to first order, we describe our perturbation by the perturbation of the metric and a vector field. And this vector field is called a Lagrangian displacement vector. And what it affects, you can think of it as you push your fluid elements along this vector a little bit in your perturbation. You then can discuss two sorts of perturbations. The little delta of Q is called an Eulerian perturbation, and that just compares fields at fixed points on the manifold. So your total field would be Q of 0 plus lambda times delta Q. And then you can also talk about a Lagrangian perturbation, which compares fields at fixed fluid elements. So what you have automatically is that S and N have 0 Lagrangian perturbation. And that just means we're pushing our fluid elements around and we're not adding any matter or entropy. So it's a somewhat restrictive formulation, but it allows you to write a Lagrangian. Okay, now moving on to equilibrium. We're going to say that a solution is in dynamical equilibrium if and only if it is stationary and axis symmetric. So a star would typically fall into this. And then for such configurations, the fluid pore velocity has to be proportional to this vector v, which is just the sum of the time-like filling vector and the rotational filling vector times a rotational velocity, which doesn't have to be uniform. And then for configurations in dynamical equilibrium, Ayer derived a first law of black hole mechanics, and for our purposes, I'm going to write this down but not include black holes, which just says that if you consider a perturbation, then the change in the ADM mass can be related to an integral of the change in N, S, and the angular momentum here. So the diagram I have in mind is here's a space-time diagram for a star. Here's the star, here's infinity, spatial infinity. And we are doing an integral over a slice, a space-like slice like this. So in the presence of black holes, which I'm not including, you would get contributions from the black hole area in the angular momentum. So that's why I'm calling it a black hole. First law of black hole thermodynamics.
Can we go back one slide?
Yes.
I'm not sure that that's the most general form of velocity. You can have colloidal velocity.
Well, I'm saying stationary and axisymmetric. Well, this is what we're referring to as stationary and axisymmetric.
Let's say in some meridian circulation is stationary and axisymmetric, but it has colloidal component.
Yeah, no, I guess you could also have that, but we're restricting to this sort of configuration for our purposes.
But then, when you restrict your stability analysis to a much narrower set of fluctuations, you cannot make a conclusion about general stability.
Well, you can talk about stability off of those sorts of situations. I mean, you'll see that we have to restrict our class of perturbations somewhat further. I mean, it'd be nicer to generalize things, but at this point, you're kind of restricted to this situation. Let me think a bit more for a second. Yeah, I mean, you could probably have that, but I think the analysis isn't going to work for that. You'll see what I'll have to do further down. Yeah. Okay, so to address stability now, we're going to try to define a canonical energy on our perturbations. And so yeah, we have two things you have to do, is introduce a canonical energy and restrict this class of perturbations. So in order to make a stability argument, I mean, this is kind of a key slide for the stability. We need the canonical energy to be conserved, meaning that if I were to integrate along this slice versus integrate along this slice, the canonical energy is the same. And we also have to have positive flux at null infinity, namely that energy can flow out here and you lose energy. And it has to be non-degenerate except on stationary solutions. So if these three requirements hold, then you have two possibilities. Either the canonical energy is greater than or equal to 0 for all delta phi, which then means that if we compare the canonical energy on this slice versus this slice, it can only decrease, and it's decreasing towards 0, which is a stationary solution. So we're going to say in that case it's stable. And the alternative is that there exists some delta phi such that E of delta phi is negative. So we still have to have it decrease. It can't be decreasing towards a stationary solution, so it's decreasing arbitrarily in our solutions growing in time. So then in that case we say it's unstable. To define canonical energy, we have to be, this is why I introduced all this Lagrangian stuff, you have to vary your, you get it from the Lagrangian. So here I'm just varying the Lagrangian, and this is kind of why I'm using a 4 form as opposed to integrating things, because now we get, from the variation of Lagrangian, you get the equations of motion times delta phi plus d of theta, where theta is this symplectic potential. This is a boundary term you would typically drop when studying Lagrangians. Then we define a quantity called the symplectic current, like so, and then the symplectic form is the integral of omega over this slice. And then we finally define the canonical energy to be the symplectic form evaluated on delta phi and the time derivative of delta phi. And we want to check then that we can choose a subspace of the perturbations such that E satisfies those requirements I set out here. Okay, well, I don't know how I should go through it. Well, I'll go through it quickly. First off, it's conserved. The reason is that you can derive this identity for the symplectic current, and if delta phi satisfies the linearized equation, then so does Lie T delta phi, which means that these two terms vanish and omega is closed, and then you can see that since it's closed, E is conserved. The positive flux is, you can show that when you impose appropriate fall-off conditions on the field. And then finally, this non-degeneracy except on stationary perturbations. This is a lot of work to show, but you can show that it holds precisely if you restrict to perturbations which are, I'll skip that. Really what it reduces to is you have to say your perturbations don't change the angular momentum of each fluid element, and they don't change the total linear momentum. And then it boils down to you have this theorem that if T is a set of axisymmetric perturbations off of a solution in dynamical equilibrium, such that the linear momentum, the entropy per particle, the particle number density, the specific angular momentum per particle, all those things vanish, then we're going to consider delta phi in T. If E is greater than or equal to 0 for all delta phi, then it's stable, and if it's negative, then there's instability. Okay. Now, this is the other main part of the calculation. We want an expression that looks like this. We want to relate this E that I've derived already to these second order quantities here. So, yeah, the tricky thing is, this canonical energy is quadratic in first order perturbations, and these are all second order perturbations. And you might think, well, how could this even possibly hold? Because there's more than one second order perturbation for a given first order perturbation. But the point is the difference between second order perturbations satisfies the first order equation of motion, and this has to vanish because of the first law in that situation. So we can derive that. I'm not going to go through the whole proof. Well, I can say this bit. This is a kind of a trick which we use in the black hole case, but only applies partially in our case. Namely, we want to evaluate omega of delta phi and Lie T delta phi. But we're going to consider instead just the gravitational part of the Lagrangian. And in that case, we can write it in this form, because if we take dd lambda of any quantity but this, and we evaluate on a stationary background, this has to vanish. But it's not necessarily true that the matter fields, that they're stationary in a stationary situation. Anyway, after a lot of work, you can eventually show that E is equal to delta squared m, second order change in the canonical energy, plus this integral involving second order quantities. Now, so this is the result. Shifting gears very quickly, we can move on to thermodynamic equilibrium. So the definition of thermodynamic equilibrium is that a dynamical equilibrium configuration is in thermodynamic equilibrium if and only if delta S vanishes with respect to all perturbations to keep the total ADM quantities fixed. And then you can prove from that that a dynamical equilibrium configuration is in thermodynamic equilibrium if and only if the redshifted temperature, the redshifted chemical potential, and the rotation are uniform. And to prove this, we use the first law. And finally, thermodynamic stability is, we say that a thermodynamic equilibrium configuration is thermodynamically stable if the second order change of entropy is negative with respect to all perturbations that keep the total quantities fixed. And so going back to your question about other fields, we're going to have to restrict to thermodynamical equilibrium configurations which have a uniform temperature, uniform rotation. So even if I started with colloidal fields, those would be ruled out by this thermodynamic requirement. So anyways, what you can derive then for thermodynamic stability is that an equilibrium configuration is thermodynamically stable if and only if this combination of second order quantities is positive with respect to all perturbations which have vanishing ABM changes, first order changes in ABM. So this is equivalent. So then finally, recalling we got this result earlier for dynamical stability for the canonical energy. If we restrict to thermodynamic equilibrium configurations, then mu, t, and omega are constant. We can pull them out of the integral, rewrite it like this, and then finally we have our main result, which is that for a background in thermodynamic equilibrium, for any axisymmetric perturbation with these constraints, both thermodynamic and dynamic stability are equivalent to the positive definiteness of this canonical energy. And there's ways which we are wondering about how to generalize, but in the amount of time, so thanks.
Is there any questions?
Are these thermodynamic stability discussions known to the users like dynamic stability discussions and linear configuration for all sorts of hydrogen and black?
Sir, I couldn't.
Are these thermodynamic discussions on the stability, are they known to produce linear configuration discussions for all sorts of higher-dimensional black hole solutions?
They'll apply to higher dimensional. I mean, so you're asking about the earlier paper. That will, yeah, that will apply to higher dimensions provided you have axisymmetry and axisymmetric perturbations. So it applies to, for example, the Schwarzschild black ring is minimum 5 dimensions and applies to that case.
So it also reproduces the Gregory stability.
The what?
The
Yeah, that's exactly an easier way of proving the Gregory-Laflamme stability. I mean, it's all linear perturbations, but like, yeah. So ideally, you could apply this to stars to find stability properties in an easier way than looking at equation motion.
Any more questions? Okay, if not, then we thank Stephen again. And I think we are going for a study coffee now, and we come back here.